A-level specification, Mathematics A, for OCR. Today we're just going to do A and B. We'll leave C and D as a video for another day. But I really want to get into how A and B work, and we'll try to do them thoroughly. So 1.01 is all about proofs. Basically, being given a statement or some statements, and with some logical reasoning, deduce that they are true or false. Let's get into it. So A says, understand and be able to use the structure of mathematical proof proceeding from given assumptions through a series of logical steps to conclusion. In particular, learners should use methods of proof including proof by deduction and proof by exhaustion. So a proof by deduction is when you have two statements, statement 1 and statement 2, and you're trying to prove statement 2 by using statement 1. Things you need to know are knowing how to express words about numbers algebraically, knowing how to factorize, and how to connect statements. Examples of the first point here is knowing how to express something like an odd number algebraically. So an odd number is not an even number. So going to the next point, an even number is always a multiple of 2. An odd number, however, since you're adding 1 to an even number, that negates it from being even. A square number and a cube number. So one thing we need to know is how to factorize. Examples of this is, at the very basic, we could say finding something that two numbers have in common and factoring it out. Here we've got 4n plus 8, which are both multiples of 4. I've taken the 4 out of the 8 here. And taking them both out will give you 4, all multiplied by, in brackets, n plus 2. Similarly for 3n plus 9, you see that they both have 3 in common, and you get 3 times n plus 3. Now this is a bit of a difficult example. However, if you've done GCSE maths, you should see how we've done this factorization. One thing students tend to trip up on is seeing the n squared and a 3n but no number next to it, and forgetting how to factorize that. However, this shouldn't trip you up too much. What we've got here is a 4n plus 8. We look at a similar way and with similar logic and see that they both have n in common. You take n out of both and you have n plus 3 multiplied by n. Moving down a little bit, we also need to know how to connect statements. Now, this is what you typically see in an exam, although this, I must admit, this is a bit of an easy example, just to get the logic and, the proper functionality of how to do the question. We're going to do this. So prove the sum of an even number and an odd number is an odd number. Looking at statement 3 here, how to connect statements. So we've got statement 1, which is sum of an even number, and statement 2, odd number. Now, like we know from our little chart here, we can express an even number as 2n and an odd number as 2n plus 1. However, here we've written m as opposed to n because we don't know that the odd number that we have in the question is specifically the one after the even number. So we can't use 2n plus 1. Statement 2 is just another odd number, 2p plus 1. Now, we've got statement 1 here. The sum of an even number and an odd number, 2n plus 2n plus 1. And we've tried to factorize out of it. Now, what can we factorize? We know that this has a 2 and this has a 2. So we've just taken the 2 out here. And you end up with 2 multiplied by n plus 1. Now, since we can choose p to be any integer, including n plus m, we can connect these two statements. And with that, we are done, because we've proven that the sum of an even number and an odd number is an odd number. We've done proof by deduction. Let's take a look at proof by exhaustion. Now, proof by exhaustion is a little bit easier than doing a proof by deduction. All you have to do is exhaust all options of a statement so that there are no options left. Best way to do this is probably through an example. Now, our example here says that 31 is a prime number. And a prime is a number that's only divisible by itself and the number 1. Now, we're going to check a couple numbers and see if they match our definition. We'll start off with 2. 31 divided by 2 is 15.5, which is not a whole number, so 2 doesn't disprove our statement. 31 divided by 3 is 10.30 occurring. This doesn't disprove the statement either. 31 divided by 4, there's no need to do it since 2 is a multiple. Since 4 is divisible by 2, so there's no need to do that. 31 divided by 5 is 6.2, which is not a whole. 31 divided by 6 doesn't need to be done since we use the same argument as with 4. 31 divided by 7 is 4.42857 to 5 decimal places, which is not a whole. 31 divided by 11 is 2.81 reoccurring, not a whole. 31 divided by 13 is 2.38462 to 5 decimal places. Now, there's no need to do any primes bigger than half of 31, because if it's not divisible by 2, it's not going to be divisible by any numbers bigger than half of itself. Now, since we've exhausted all the options, there's nothing left to do, and we can confirm that 31 is a prime number. We've proven the whole of A. Let's look at B. Understand and be able to use the logical connectives. Congruence implies that and if and only if. Learners should be familiar with the language associated with the logical connectives. Congruence, if blah blah blah, then blah blah blah, and if and only if. Now, congruence is the first statement. Well, the first thing we're going to look at. It comes from the Latin word congruo, which means I meet together or unite with someone, or agree or coincide. Now, at GCSE, when you had congruence, you usually looked at triangles or similar shapes that had two sides and an angle in common, and therefore will be congruent to each other. However, A-level is a little bit different. We're going to look at two statements which essentially mean the same thing. Here we got n is an even number. That's the same thing as saying as n is a multiple of 2. Or n is an odd number is the same thing as saying that n is not a multiple of 2. Now, that's not the same as if and only if, because we're not making any connective arguments between the two. These statements are just simply the same. We haven't made any intelligent links between them. For implies that, or if yada yada yada, then blah blah blah, which is a symbol used here. We can look at it this way with an example. Prove if n is an even number, then the square of n is even. So what you essentially want to do is take one statement and then connect it with another statement using then, and then prove that from statement A you can go to statement B. Now, step one is you want to put words into numbers. Here we have n as an even number. That in words into numbers, means that the first statement is just saying 2n. This is an even number. Next statement is the square of n is even, which means you can express it as 2p. Step 2, you want to take the command given, for example, the square, and you want to execute it. So you have 2n squared. 2n squared is 2n multiplied by 2n, which is 2 times 2, which is 4, then n times n, which is n squared. Step 3 is that you want to factorize and compare. Now, we have the 4n squared here. We can take the 2 out, and 2 is right here. Now, 2n squared is just an integer, so I'm going to express it as p. Now, if we go back to the first statement, we can see that 2n is the same as 2p. So we're done. An if and only if statement is like having two implies that, or two if then statements going both ways. For example, you have n is even if and only if the square of n is even. You essentially want to prove if n is even, then the square of n is even, and if the square of n is even, then n is even. So first of all, you convert it into a if and then statement, and you reverse it, so essentially make the qn and pn reverse their roles. Then you prove the pn implies that qn statement. I'll leave that as an exercise for you, because if you can do the if then statement above, then you can do this as well. It's just doing the same thing twice. That's A and B done. Hopefully we'll get C and D done tomorrow with examples as well. Just as a quick recap, let's go over them. So today we've understood how to construct a proof by deduction and by exhaustion. And we've also learned some connective statements, the congruence statement, the if and then statement, and the if and only if statement, and the differences between them.